there, there. Okay, here we go. I will do my best. Try to pay attention because it's not the easiest thing to explain and not the easiest thing to understand. All right, summation notation allows us to write a long sum into a single expression. While summation notation is used out throughout math, we want to focus on how to write it with Riemann sums. Okay, so here's our example. We want to find the area under this curve from 0.5 to 3.5. Okay, so we're going to use a Riemann sum. Now, we want to get really accurate, and that's what our point is. We want to make, instead of using rectangles, we want this to be smooth. Okay, we want it just to be a smooth line so we get the exact amount. And that's the process we're going through to get to there. Okay, so let's say we'd use a right Riemann sum because that's a little easier to use than a left in this situation. Okay, so if we're using a right Riemann sum and we say we want 4 rectangles from 0.5 to 3.5. Okay, so we make 4 rectangles. Okay, what's the problem with making 4 rectangles from 0.5 to 3.5? Yeah, you're not using whole numbers. Okay, but they did it for a fact so then you can see the 0.75 involved. So each of these is 0.75 wide. And the height depends on where we're at this point, this point, this point, and this point. Okay? All right. So, right now we have 4 rectangles. Let's say we had 144 rectangles. Would it be easy to add up the way we were doing it with the trapezoidal sums and midpoint sums if we had 144 rectangles? No. So that's why we're using summation notation, because your calculators can do summation notation. And I'll show you that after a little while. So that'll help out things a little bit for some questions. Okay? So we have rectangle A1 standing for area 1, area 2, area 3, area 4 for this. Okay? So area 1 plus 2 plus 3 plus 4 equals the whole area of this, which is the summation of the 4 areas. Okay. So what we need to do is find an expression. So we know the width is 0.75. I just explained that. The height comes from the right side of the rectangle because it's a right Riemann sum. It comes from the right side of the rectangle. So we need to have x1 be the right endpoint of the ith rectangle. What's the ith rectangle? Well, it could be the first, it could be the second, it could be the third, it could be the fourth, it could be the 144th. Okay? So the ith rectangle is whichever rectangle we're coming to. Okay? So to find where this I1 is, basically, it's 0.5 plus the 0.75. Okay? To find the second rectangle is 0.5 plus 0.75 times 2. Because we went over 0.75 and 0.75. To find the third one is 0.5 plus 0.75 times 3, and so on. So we can get that from a summation. Multiply it by 1, multiply by 2, multiply by 3. Okay? So the function is the square root of x. That's where that square root comes from. So where we want to go from is xi. So it's 0.5 plus 0.75 times whichever term we're on. 0.75 times 1 puts us there. 0.75 times 2 puts us there, and so on. Okay? So the area of a rectangle is the width times the height. Here's our width. Here's our height. So then we put it in summation notation, which is right here. That's summation notation for finding the area of this right Riemann sum. Okay? So the width times the height. And the height always goes from the function that we're given. the function is y equals the square root of x. So it's the square root of where we are at underneath the function on the right side of the rectangle. All right, not the easiest to understand. The great thing is Sal Khan explains all this stuff in his videos too. So if you don't get it from me, because I might not explain it the greatest, you can always watch Sal and get it in his words, and between the two of us, you can kind of hopefully make sense of this. Okay? All right. So, the process. What we have to do is find the width, the change in x. To find the change of x, we find the end point and the first point and divide it by the number of rectangles we use. Okay? The furthest right point, the furthest left point divided by the number of rectangles we use gives us the width. Okay? And then we have to figure out if it's a right Riemann sum where the right endpoint is. Wherever we start plus how much we move by which times which rectangle it is. Okay? So then we get the height of the rectangle, and the width times the height is our area. And then we put that sum and we make it into a Riemann sum. Here's our right Riemann sum. Our left Riemann sum is a little different because when you go from the left side, we make I equals 0 and go to n minus 1 because it's to the left, not to the right. So we have to subtract off one value of it. So if we subtract off one value, 1 becomes 0 and n becomes n minus 1. Okay? So looking at this one, yeah, and it's a trig one, which is not so bad. Looking at the rectangles, do they look like a right Riemann sum or a left Riemann sum? Right, because at the right side of the angle, the right side of the rectangle, that's where it hits the function. It hits it at the right side. Okay? So where do we start at? Well, we start at way in between negative 1/5 pi and negative 2/5 pi, which is negative 3/10 pi. Okay? And we go up to 2/5 pi. Okay? So we go from negative 3/10 pi to, I wonder if they have a mistake. It says 1/2 pi. Oh, yes. Because here there's not a, okay, we go to there. Sorry. We go to 1/2 pi, which is right there, which is because halfway in between 2/5 and 3/5 is 4/10, and 6/10 is 5/10, which is 1/2 pi. There's no rectangle here. Why? Because it hits 0 on the right side. So there's not going to be a rectangle there. Okay? So, since it's a right Riemann sum, which would make sense out of these choices for that. Well, we know with it being a right Riemann sum, it's not going to be this one, and it's not going to be this one. Okay? Because those are left Riemann sums. So we need 8 equal subdivisions to go from there to there. Okay? So how wide are these? Well, we go 1/2 pi minus a negative 3/10 pi divided by 8 rectangles. Well, we go plus a positive. This is 5/10 plus 3/10 is 8 pi over 10 divided by 8. So 8 is really 8 over 1, so if we multiply by the reciprocal of the denominator, the 8's cancel, and it's pi over 10. That's the width of each of these is pi over 10. That's why it has pi over 10 for all these. Okay? Now we got to figure out the height. Well, we start out at a negative 3 pi over 10, plus we go another pi over 10 times I. Okay? Because we start at negative 3/10 pi, and we go the width of it to find the first one, and then we go up, and we say the cosine of that. Okay, the cosine of that. Well, which one says that? Well, negative 3/10 pi, that, it is choice D. Yeah, I've been doing calculus for a few years and it just takes me a little bit. So for you guys seeing it for the first time, I'm sure it's like whoosh, a little bit, right? But hopefully you're getting a little bit of this is the width, this is the height, okay? From here to here, this is the height. And then the summation makes how many rectangles we have. Okay. So looking at this one, how many rectangles do we have? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 rectangles, so there are 9 subdivisions. Okay? We go from 0 to 3. Well, what's 3 minus 0 divided by 9? 1/3. So each of these rectangles is 1/3 wide, as we can see from the bottom of this. And maybe you guys can't see that because it's too small a font. But each of these is 1/3. So our width equals 1/3. Okay, what kind of Riemann sum we using? Oh, we're using a midpoint Riemann sum, which makes it even more fun. So we got to go in the middle of this. Okay, so it's 1/3. Basically, it's 1/3 minus halfway, which is 1/6. Okay, 1/3 minus 1/6 to get me at 1/6. So that's 1/6. This is 2/6. And then next I have to get to 3/6. Well, what's 3/6? So it's 1/3 plus 1/6. And then I have to get to 5/6. So then it's 1/3 plus plus how many sixths? 1/3 is 2/6. And I want to get to 5/6, so I want to get to 3/6. So I add 3/6. What's happening each time if I'm at negative 1/6, then 1/6, then 3/6? How many sixths am I adding? I'm adding 2/6, which is 1/3. So basically, I'm taking 1/3 minus 1/3. No, I'm adding, okay. Think through this, Mr. Bierschbach. All right. So I'm adding 2/6, which is 1/3 each time. So instead of starting at 1/3, it would be more appropriate to start down here and then take the, come on, take the 0 plus 1/6, so I don't have that minus sign, and 1 times 1/3 plus 1/6, or else plus 3/6, and then we go plus 5/6, 0 plus 3/6, 0 plus 5/6, and so on. Okay? So it'd be good to start at 0 each time. So I'm starting at 0. So you can see I equals 0 here. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9 subdivisions. So if I have 9 subdivisions, if you count 0, 1, 2, 3, 4, 5, 6, 7, 8, that's 9 subdivisions, right? So it can't have a 9 on the top because that would be 10 subdivisions. So it has to be one of these two. Okay. Okay. So putting this all in here, what's our function? Okay, it's negative 1 over whatever I come up with here, which is what I'm struggling with right now, minus 4 times the width of 1/3. Okay? So I got to get the right function in here to make that deals with our i's, because I starts at 0, and then it goes to 1, and then it goes to 2, and then it goes to 3. So 0 gives me 1/6. So if I put in 0 times something plus 1/6, and then 1 times something plus 1/6 to get me 3 to 3/6, and then 2 times something plus 1/6 to get me 5/6. So this is like, this has to be 0/3, 1/3, 2/3. Because 2/3, wait, I'm, I over 3. So if I is there, 1/3 plus 1/6 would make work. And I over 3. So 2/3 plus 1/6 is 5/6, right? So if this is I over 3 plus 1/6, would that work? Because that would make it 1/6 there. And then 1/3 plus 1/6 is 3/6, which is there. Yeah, there we go. I over 3 plus 1/6. Hoofda. That was hard to get. Okay, so this is summation. But none of them look like this, right? So we have to multiply through our 3. So let's multiply through with our 3. So if we multiply our 3 through, we get I plus 3/6, which is 1/2, minus 12. Okay? And then if I get rid of my denominator, because I have a complex fraction here, if I multiply both the top and the bottom by 2, I get negative of 2 over 2i plus 1 minus 24, which is negative 2 over 2i minus 23. There we go. It's D, which is the right answer. Oofda, right? All right. So, how does that work with what we're trying to do with Riemann sums? Well, here's a function. If we want to find the exact area under this, we're going to use what is called an integral. Because Gottfried Leibniz was using summations, and then he said, you know, I'm just going to go like this. The guy who invented calculus, he said, I'm going to use this instead of that. Okay? Type of thing. Because it's a little different than a summation. Okay? So, how does this work? Well, let's say that between 2 and 6, we want to find the exact area. Okay? So this is obviously going to be an overestimate if we use a right Riemann sum. Okay? But this is a way overestimate with one rectangle. But watch what happens. Watch this, people. Come on. Go to the hyperlink. Got to flip my computer like this. Then I'll go to the hyperlink. Okay, watch. We start with one rectangle. And, ooh, the more rectangles we get, the more accurate we get. So then we went from one rectangle to 100 rectangles. And even with 100 rectangles, we're going to be a tiny bit off, but just barely off. Okay? So, what does that remind you of from first semester of going from going and keeping going till it's so small that we can't do it anymore? Oh, it would be a limit when we keep getting closer and closer and closer and closer and closer. Yeah, and the limit of the function will make basically an integral. And an integral will give us an exact value of this. And that's what we're working towards. But since I've talked way too long, I'm going to